And we're back with talk number 3. Olek Gierczak with gradually typed languages should be vigilant.
Thank you very much. So today I'll be presenting our new gradual typing correctness property, which we call vigilance. So to start, in gradual typed languages, you have fine-grained interop between typed and untyped code. So how that comes about oftentimes is you have an untyped language that decides, okay, we want to adopt typing. We want to let users add type annotation to their program. So like in this example, we have both an argument and a result annotation on this function. However, there becomes a problem, which is that as soon as the language designers do this, well, they have a whole standard library that's untyped. And now they're kind of forced so that if users really want to use types throughout their program, they're going to have to somehow quickly give them access to these libraries while also having types. So a common solution here is that you make this typed interface. So here, this untyped user is calling a function, a segment PNG function from a typed library, but they don't necessarily know. But the library designers decided we're going to add types to this later, and instead just call a untyped segment function. And then that value flows back to the untyped user, and the untyped user expects this to do exactly what the type tells them, which is return some kind of pair of PNG. Now the problem is, what if this untyped library is buggy and sometimes doesn't return PNGs, but maybe returns, JPEGs in some cases? So the question is, what does the user actually see now? And the answer is, it depends on the cast enforcement strategy. So in one case, in the natural semantics implemented in typed racket, they actually see the PNG cross PNG no matter what. And the way that natural does this is they have higher order contracts that wrap functions, and they perform so-called deep checks, ensuring every single type is accurate. There's another semantics called transient, implemented in a system called reticulated Python, and they just check the top level type constructor, just shallow checks, but they make sure they check enough so that they can ensure safety. So in that case, the user only knows that they're going to see a pair, but they know when they do more stuff with it, every interaction will be safe. And finally, there's erasure, implemented in TypeScript, and this is just the case where you have no checks and the user sees this as documentation, but they have no dynamic guarantees that they actually will see a pair of PNGs. In general, it turns out that this corresponds directly to different type soundness theorems. So Greenman and Felissen showed that there's actually a spectrum of type soundness theorems depending on the operational semantics. So from the same statically typed term, depending on whether you're using the natural, transient, or erasure operational semantics, you'll get either a type, a tag, top-level type constructor, or dynamic soundness theorem. And to make matters worse, it turns out that type soundness is not even enough, because they showed that there's another operational semantics that's error equivalent to transient and yet has the same kind of type soundness guarantee as natural, which is quite odd. And to make matters even worse, let's go back to our untyped user program. At the end of the day, this chopped function is untyped. Even though they're inside the function calling this typed function segment PNG, the outer function itself, if somebody else calls chopped, all they know about it from soundness is that it behaves like untyped. So if you have a semantics that forgets casts after some amount of casts back to dynamic, then the user doesn't get this guarantee anymore that they're actually going to see pairs of PNGs. So how can we go beyond this? So let's see what exactly happens as we flow values through this program. The user takes an image and sends it to segment PNG. In segment PNG, we see this PNG annotation. So this becomes kind of an assertion that the user has that the image better be a PNG. And then that gets sent into segment. Segment produces some value after running. And when it goes back to segment PNG, it sees the annotation and sees this value better be a pair of PNGs. And finally, it goes back to the untyped chop function. So over time, we see as we run a gradual program, we get these kinds of assertions like image better be PNG and V better be a pair of PNG. So now there's the question of how do we know these insertions are actually enforced? In the prior work, complete monitoring, they prove a syntactic theorem that basically says that at every one of these type assertions, there is some check that happens. However, because it's syntactic, they actually don't have a way to precisely say what those checks are. So at best, they can say that some check happens. So in particular, there can be languages that have checks that always succeed, and that can still be a complete monitor. So it's not quite the property we're looking for here. So in general, we can try to do a bit better by saying, OK, as a value flows, it accumulates type assertions. So let's collect them all. Let's give that a name. So for example, if we have some blue chunk of code, and it produces a value at type tau1, then that value flows into some purple chunk. Now we know not only should it behave like tau1, but it should also behave like tau2. And as it flows into this red chunk, we accumulate an additional tau3, and into the green chunk, we get tau4, etc. So let's call this list of types a typing history. And now we have more precise language to say what we want. We want to say that a value behaves like its typing history. Okay? Now the question is, what does behaves like mean? And this is kind of the key idea that formally supports our approach. We're going to use a semantic model to specify that precisely. So now we can introduce vigilance, and we'll say a type system in operational semantics is vigilant when every runtime value behaves like its typing history. Okay, so there's a couple things to tease apart here. Exactly what do we mean by behaves like a type? How do we know what typing history is associated with a runtime value? And what does it mean to behave like a typing history? So starting with behaves like a type, we're going to use a particular kind of semantic model called a type soundness logical relation. And the key idea is that we're going to have essentially two sets for every type. A value relation, so we'll say that a value is in the value relation at tau when that value behaves like tau. And then similarly for expressions, we're going to have an expression relation, which is expressions that run to a value that behaves like tau. So that calls back into the value relation. OK. Now from here, to actually collect up those typing histories, every time a value crosses a cast, we're going to accumulate the boundary types on those casts. So if we know that V has a typing history tau bar, and we see that we cast it to tau prime from tau, we're going to add those two types, tau prime and tau, into that typing history. But how exactly do we have that association in the first place? Well, we're going to instrument our operational semantics to label every value and track values and types in what we call a value log. So we're going to use sigma for that value log, and the type is going to be mapping locations to values and optionally pairs of types. So why an option? To begin with, let's consider the case before where we have this value running from this blue component. In this case, this blue function hasn't introduced any casts. It's just a single chunk of code that runs down to value. We don't know any types yet, so we just put in none. Now this value gets sent into this purple code, and now we get an additional type tau2 from tau1, and now we annotate that new value in a new label along with these types. And similarly, as we go into the red chunk, we get a new label and a new type, and so on and so forth. OK, so we have some instrumentation here. How do we incorporate this into the logical relation? How do we get to typing histories? So we notice something, which is that a value log is kind of like a store. And so we can use a very common technique in logical relations, which is that we'll add a store typing into our semantics, which tells us what the type is for every location. But in this case, we're actually going to associate every location with the typing history itself. So now we'll have two additional members of our logical relation. We'll have the store typing, the value log typing, and the value log itself. OK. So that's how we get to typing histories, but we still have one more component, which is what does it mean to behave like a typing history? And to do this, we introduce this notion of a value history relation. So it's supposed to be the whole typing, basically the value relation extended to the whole typing history. And it's basically the same as just saying that the value satisfies every type, or the value behaves like every type. And finally, we can say the formal statement of vigilance, which is that a language is vigilant when, for any well-typed E at type tau, then it is in the expression relation at tau with empty value log and value log typing. And we can extend this to open terms in the completely usual way. And stepping back, summarizing, we now have a bit of a recipe for vigilance, which is that if you have a type system in operational semantics and you want to show that it's vigilant, well, you're going to start with a type soundness logical relation. You're going to instrument your operational semantics with a value log. And then you're going to add the value log and value log typings to your logical relation. And finally, you're going to require every label in your value log satisfies its typing history. OK, so now that we have vigilance, we can ask what satisfies vigilance. And it turns out there's a spectrum, just kind of like type soundness, which makes sense because we built on top of type soundness. So similarly, we have a dynamic vigilance for erasure. We have a tag vigilance for transient, and we have a type vigilance for natural. But importantly, this is enough to distinguish amnesic from transient. They don't have the same vigilance property. So looking at this, we kind of wanted to perform a design exercise, which is, can we do any better for transient? Because we were noticing something while looking at transient programs. So transient performs tag checks on casts and elimination forms. And that's key to the safety property. But it also means there's something more interesting going on than just the top-level type constructor. So in this example, we're taking in a pair of PNGs and returning a PNG. And we're just taking the first projection. So because of the essentially tag soundness result, all we know about the argument coming in is that it's a pair. However, on the first projection, we do this check that actually gives us more information about what's in that pair, namely that it's now a PNG. So using this kind of idea, we can actually show that many programs with under transient have much stronger types than just the tag. So for example, in this program, it's not just a pair, it is a pair of actual nat and int, because we can just examine in the first case that the only way this can run to something that's not an error is if it's a nat. And in the second case, it's definitely an int. Doesn't matter how many checks go. So Greenman-Fleisen said, OK, transient satisfies tag, but we want something truer to the behavior of transient. So we designed this truer transient type system. And the key ideas are that on introduction forms, we remember the type information we've had. And on elimination forms, we learn type information. So in the case of remembering, if we have a pair, we actually remember, in the case where the first component's an int and the second component's a nat, we don't just say pair, we say int cross nat in the normal semantic way. And on elimination forms, we look at that check on that projection and actually learn additional information about the type that sits there. And so the key to this is a lattice of types. And the idea is at the top of the lattice is the least precise behavior, and at the bottom is the most. So when we say learn type information, we mean meeting in this lattice. So notably, we have a dynamic type, which is our top least precise behavior. It captures all of the behavior you could possibly have any term. And then we have the bottom, which is the most precise, which is terms that definitely err. So there's no value that satisfies the bottom type. So that is definitely going to error because of some cast. Now we also have that ints can be refined into nats. We have that pairs, unsurprisingly, are component-wise. But on functions, we have something a little weird, which is that they always have the argument star, which for people kind of used to type precision, this might be a little bit surprising. And the key idea here is we're talking about transient behavior. And when you talk about semantics, semantic subtyping is a contravariant notion, not a covariant notion. And it's really intuitive in the sense that if you have a function that takes in nats and returns nats, then you just know it can take in nats. But if you have a function that can take in a star, you can always treat it like a nat arrow a function that takes in nats, but it can take in ints, and it can take in bools, and it can take in functions, and whatever you want. And it'll still act safely. So that's the idea here. Any transient function is actually safe when applied to any argument, which is kind of a surprising result that we think people didn't really emphasize enough. But anyway, moving on from here. After we developed this type system, we actually noticed that you can perform a very simple operation, which is that if we don't learn anything on a check, which is kind of like saying we do a meet and it just ends up at identity, it didn't move your position in the lattice, we can just remove that check because it's effectively a no-op, right? And it turns out just this grabs almost all of the optimizations in a previous paper, which we found was quite interesting. So it turns out that just having this little bit of flow sensitivity in the type system kind of like made optimizations come for free. Okay, so back to our spectrum. We've added a new position, namely that transient is vigilant for truer types. And moving on to future work, my next project basically is to look at gradual borrowing and see what vigilance means in that context. We also have a conjecture that abstracting gradual typing produces vigilant languages by construction, and we'd love to see if that's true. And I also have interest in thinking about optimizations from the perspective of typing histories. So in summary, vigilance describes what types are enforced at runtime using a type history. And the fact that it's semantic means that vigilance prescribes behavior, not necessarily just checks. And if you want to see the paper and more, you can check my website, olek.pl. Thank you.
Thanks, Olek. Do you have any questions?
Hi, thank you so much. This is awesome work. I'm curious how this idea extends to, how it would extend to situations where you can have like closures over mutable variables. So in the case where you have some variable, it goes through a bunch of casts. We accrue this typing history for it. And then it is captured by a different function. There's some mutation that happens, may or may not invalidate some of those casts, or some of the things in the typing history, right? Do you have any thoughts on like how, or I guess, does this paper address that case? And if not, do you have any general thoughts on how that could be handled?
The paper does not address that in particular. I think, so if you take the case of something like a monotonic references, then the problem is solved for free because it's by default. My conjecture is that you need some amount of indirection, some extra indirection in the typing history, so that it wouldn't just be types, but like you could have some, section that might get cleared out a bit after the mutation, and then build up new types as you get new assumptions. Yeah.
And then I had one other question, which is with the typing history, since you kind of have this rich and flow-based log, I guess, of all the places the type has been and various assumptions that were made about it in elimination forms. Given that you have that information, if you wanted to give an error message or show blame or something for a type error, right? What kinds of interesting things could you potentially do, given that you could say, oh, it violated this assumption that happened at this time, but not these others?
Yeah. So blame is something kind of that we didn't cover at all, and we do feel like there seems to be some like very strong connections we could make. My feeling is that the typing history should, like the semantic idea of why you wouldn't satisfy a typing history should basically exactly align with that error. And so if we enrich the typing histories with more source information, we kind of feel like that should give you a blame correctness theorem as well. But it's stuff we haven't explored yet. Thank you.